here's a cool little project, building a joystick-controlled stepper motor laser turret. In this video, I'm going to go over wiring and programming the X-axis motor, and by the end of this video, I should be able to control the left and right motion with the joystick. But first, here's a list of some of the things I'm going to be using. A NEMA 17 stepper motor, an A4988 motor driver, and an Arduino-styled microcontroller called the Elegoo Mega 2560. I'm going to need a breadboard, DuPont wires, and a thumb joystick. And finally, I need a power supply. Alright, a good first step is to set the current limit on the motor driver to keep it from overheating. And to do this, I'm going to make an adjustment on the potentiometer on my motor drivers. The first thing I'm going to do is I'm going to take a black DuPont wire and I'm going to connect it to the ground pin of my Arduino. And I'm going to take a second wire. Red is going to go to the 5 volts out of my Arduino. And again, the black wire is going to go to the ground pin of the Arduino, and the red is going to go to the voltage in, or the VDD pin of the motor driver. Then I'm going to take another black wire, and this is going to give me my common ground so I can take this measurement. I'm going to connect it to the second ground of the Arduino board and clip the alligator clip, the black one. That's my return, so I can take this measurement. And finally, I'm going to take the alligator clip from the red wire, connect it to my screwdriver, and then set my digital multimeter to take a DC measurement. I'm going to give the Arduino some power using a 9-volt battery so we can make this adjustment. All right, as soon as that screwdriver touches the metal potentiometer, I'm going to get a reading of about 900 millivolts, and I'm going to go ahead and crank that up to about 1 volt. And using math, 1 volt reading should give me about 1.25 amp current limit. Now my motor drivers are rated for 1.5 amps, so 1.25 current limit should be plenty for this project. All right, now that current limit calibration is done, I'm going to go ahead and remove the ground wire that I used to make that calibration. That's out of the equation. All right, let's go ahead and connect the direction pin from the motor driver. That's the DIR pin. Push that in there. I'm going to go ahead and connect that to pin 3 of my microcontroller, the Arduino. After that, I'm going to go ahead and connect another wire to the step pin of my driver. On the opposite end is going to go to pin 4. Why not? One thing, a lot of people, I've seen a lot of videos on this. There's a lot of people that they don't use the enable pin from the motor driver, but it is important. I'm going to go ahead and we're going to use the enable pin in this project. It's going to be needed. I think you're going to see why later on. We're going to go ahead and connect that enable pin from the motor driver to my controller to pin 5. We'll see how all this comes into play later on. All right, on to the stepper motor. It comes with a ribbon cable, which is keyed. Plug that in. There's 4 colors: red, green, black, and blue. It's important to note that stepper motors usually come in different phases. This is a 2-phase. When I twist the shaft, it's relatively easy to twist it. But I need to find out which wires go to each phase. So the first thing I'm going to do is connect red and green using a jumper wire, and then I'm going to twist the shaft again. I'm going to feel noticeably that it's much harder to turn that shaft, and that tells me that red and green is 1 phase. And I'm going to do the same thing with black and blue, although I already know that is the 2nd phase, and sure enough, it is hard to twist. Again, removing that jumper wire, that's easy to twist again. So now I know my phases: red and blue, red and green, and blue and black. Red and green one phase, blue and black the other. The green DuPont wire I'm going to hook to 1A, excuse me, 1B. Red is going to go to 1A, blue 2A, and black 2B. And then I just connect them to the ribbon cable according to the color. So our phases are lined up, and this motor should operate properly at this point. All right, so I have the two pins on the motor driver that we're not going to use is sleep and reset. I'm going to take this white wire and just jumper them together. Don't need them, not going to use them, but I do have to jumper them together. Next, I'm going to connect the motor driver to the power rail of the breadboard, starting with the ground next to the VMOT. I'm going to connect that to the blue rail. VMOT is your voltage for your motors, the 12 volts. And the red is going to connect to the VMOT pin, and again to the power rail to the positive side, or the red side. Now my power supply came with this banana cable, which I clipped. That's going to go into my power supply. I went ahead and cut them in half and spliced on some DuPont wires so I can plug them straight into my breadboard. And starting with black, that's going to go to the blue side, or the negative side of the power rail, and red is the positive or the red side of the power rail, and that the other end is going to connect to my 12 volt power supply. So this capacitor is good practice to put a capacitor in parallel on a DC motor because it helps reduce noise and keep out voltage spikes. This is a 25 volt electrolytic capacitor. I believe it's 330 microfarads. They are polarity. You do have to know the polarity. So went ahead and plugged that in parallel. Again, I've done this experiment without that capacitor and I haven't seen a big difference, but it is good practice to put a cap in there. Now the joystick, this is the first time I'm using DuPont wires that are male to female. So the female end goes into the ground pin of the joystick and the other end goes parallel to the ground pin of the Arduino, which is next to the VDD pin. Excuse me, Arduino. I said Arduino. I meant motor driver. So the red goes to my 5 volt on the joystick, and that's going to attach to the VDD in parallel with what's connected down there already to the motor driver. Now for control, there is another pin on the joystick, the VRX. X basically represents your x-axis, so the left and right motion of the joystick. I'm going to plug a green wire into the joystick's VRX, and the other end goes to analog in, or analog A0. It's A0 pin. And that's going to give our analog input for the joystick. So for the most part, I'm all connected. There's a few things I haven't connected yet. As you notice, I didn't connect the VRY pin from the joystick, nor did I connect the SW pin. The VRY is going to be used to control the Y-axis motor in another video, and the SW pin is going to be used to control the laser turning off and on. Again, not in this video, but next video. But now we're on to the fun part, which is programming. Very first thing I need to do is make sure that I have the correct board selected. So when I go up here to the very top, I'm going to select board, and on the search bar, I'm just going to type in the board that I'm using, which is the Mega 2560. So Mega, and it's going to pull it up right here. Click on that, and then we can start writing in our sketch. All right, at the very top, we're going to declare all of our variables. Constant integer. We're going to call them constant integer x pin is A0. That's the analog input of our joystick. And I'm going to list out a bunch of others right in a row. The direction pin being pin 3, comma, step pin is pin 4, comma, and then lastly, enable pin is pin 5. And we're going to end that with the semicolon. An unsigned long is a data type that allows the storage of a large positive integer. And we're going to call this one last step x. And we're going to set that equal to 0. And then we get to move on to the void setup, which in the void setup is a code that runs only once before it gets into the loop, which runs continuously as long as the Arduino is powered on. And here we're going to set up our pin modes all as outputs. All caps. Have to put it in capital. Case sensitive here, because if I don't put it in all caps, then it won't work. Then we're going to digital write. The enable pin is high. X enable high. And what that does is it keeps the enable pin, it keeps the motor driver turned off. So when your enable pin is high, it's off, but when it's low, the motor driver turns on and allows the 12 volts to power the motor. And that is everything we have to do for the setup. Then we move on to the void loop. All right, in the loop, the first thing we want to do is have the joystick A0 pin. We want to analog read that. Read the value at A0. And we're setting that integer to X value. Then we're going to do an unsigned long. We're going to call this current micros. And we're going to set that equal to micros. All right. What this function does is it records the current time in microseconds since the program started. Then we got to create another function called handle motor. Call it handle motor. And we're going to list out all the values from above. Current micros and 508. All right, the number 508 is the dead center position, the resting position of my joystick. If I move it to the left, it starts moving towards 0. The value starts moving lower. And if I move it to the right, it moves higher, and the high point is 1022 and the low point is 0. So when I leave it dead center resting, you would think it would be right in the middle, which is about 512. And this particular joystick, I already mapped it out to, and it's 508. But I'm going to create a dead zone in the next part. And that's basically where if you touch the joystick and you barely move it to the right or left within about a 15 unit space between right or left, it's not going to go anywhere. So you barely move it, nothing happens. It doesn't turn your motor driver on. But once you get outside of that dead zone, then the motor will start moving. And you'll see that here in a second. All right, now we're going to get outside the void loop, and we're going to create another void. and further define handle motor. We're going to assign more variables. Integer val, all kind of short, abbreviated variables for value enable. And then we want to do step, unsign long, the ampersand at last step, unsigned long, and then we're going to put a time here, which is now. The time is always now. And then the dead zone center. And we're going to open up another set of braces. Let's say within this function. Now, the just a side note, the ampersand symbol tells the Arduino that this variable should not be copied, but instead the function gets a direct link to the original variable. Without that ampersand symbol, the motor forgets when it last stepped, and the timing logic of would break and it wouldn't function. Equals. Now we're going to create the dead zone by saying the value minus the dead zone center, which calculates the distance between the joystick position and the center, the absolute value. It's always going to be a positive number. And then we're going to do our first if. The different value is less than 15. Open up another set of braces. We're going to digital write the enable pin in is high. And then lastly, we want to return, which exits the function immediately. Okay, so what this does, so the center being 508, if I move it within 15 units to the left or 15 units to the right, that creates my dead zone. And that's why I'm using absolute value. So there's no negative number. It's 15 difference to the left or 15 difference to the right. It's all in a dead zone. Basically, it gives me some wiggle room with the joystick. Now I have to program the direction. Digital write, enable, comma, low. Digital write, direction, val. Put this in parentheses within a parentheses. Less than dead zone center being the number 508. Put that in parentheses, and then this is shorthand for an if else, so I'm going to put question mark high colon low. And all right, what this line of code does is sets the direction high if the joystick reads less than 508. So if I'm going left or going to the left, it's going to go less than, it's going to set it high, which makes the motor spin counterclockwise. However, if I go to the right and I go above 508, then the direction switches to clockwise. And now we got to talk about speed. Long interval. We're going to do a map function. Map diff 15 508, which is our center. And we're going to use a big number here. It's 500,000 and 1,500. All right. What this code does is it maps the stick distance, which is 15 to 508, to a timing delay of 500,000 microseconds, which is extremely slow between steps. to 1500 microseconds, which is extremely fast. So in other words, this makes it where the motor will speed up or slow down depending on if the joystick position is barely outside of the dead zone or all the way outside the dead zone. So as I bring the joystick to the left and it gets outside the dead zone, it's going to go really slow. It's going to have a step of about 500,000 microseconds, which is sounds big, but that's half a second. Still really slow, half a second per step. And as I continue going to the left, it's going to speed up all the way down or all the way up to 1500 microseconds. So it's going to get really fast as I go left and right. These values are probably too much. It's going to be too slow and I think too fast for 1500. But I'm going to play around with these numbers for now and then we'll adjust them later on. All right, now we want to talk about the interval. We want to constrain it or keep it within those two values. So I'm just going to do a simple line here, constrain interval. Let's see, interval, comma, 1500 and 500,000. All right, and this ensures the delay never goes below 1500 or above 500,000 microseconds. Now we do another if statement. If now minus the last step is less than or equal to the interval, and we get to do another start braces. This basically sets our non-blocking timer, which checks if enough time has passed between the last step and the next step. And go last step equals now, and this updates the time step so we can wait for the next interval. And we're going to digital write step pin to high, and that sends a high pulse to the motor driver to trigger one step. Then we got to put a delay in here, microseconds. We're going to put pretty much the minimum delay. If you go any lower than 10 microseconds, you got to give time. So you basically wait 10 microseconds to ensure that the driver registers the pulse. So if you go any lower than that, it might start messing up, but it's about as low as we can go. 10 microseconds per high and low pulse. And then we're going to digital write step pin low, and that sets the pulse back to low to complete the square wave or pulse signal. That's it. That's all we got. Now we just got to compile. All right, now that the code is finished, what I'm going to do is check to make sure there's not any errors in the code. So I'm going to mouse over that check mark and click on it, and sure enough, it's going to find an error. And what it says is the X enable was not declared in the scope. And I think what they mean is I need to call that X enable pin, and we're going to go ahead and check it again. All right, it says there are no errors. So now we can upload. All right, so now I got to plug in my Arduino to the computer. I'm going to take my mouse. I'm going to mouse over that right arrow on the upper left-hand corner, and that's going to send all that code, compile it, and send it to the Arduino. All right, now with the motor driver, I went ahead and attached a flange coupling to it, so you're going to be able to see it spin as I've programmed it. But before I do that, I'm going to attach an arrow using some double-sided tape. All right, I'm going to stick that on top of the flange, and we're going to see some differences in speed here in a second. All right, plug my Arduino in, grab the joystick, and let's start moving it left and right. So you can see how fast it goes. Now I'm barely moving it to the left, so it's going counterclockwise, and you can see it almost ticking. That's how slow it is. And of course, if I go all the way, it's going extremely fast. It's going so fast that the double-sided tape doesn't stick anymore. It kind of fell off, so I'm just going to press it down there a little bit harder and keep playing with it. I want to highlight the ticking motion. All right. So as this steps at about 1.8 of a degree. So that's your a full step. As you can see, it's with full steps going all the way to the left or right. It's going very fast. But the ticking motion, let's see if I can get it down to half a second. It looks like it's ticking like a clock at half a second. And so I don't really like that. I need to get some resolution. I want to make it a little bit cleaner. So as it is right now, each time this motor takes a step, it is moving 1.8 degrees. If I wanted to focus, when I attach a laser to it, if I want to focus this laser on something up close, 1.8 degrees isn't a big deal. But if I want to focus a laser on something at a distance, I need it to be a lot tighter. I need every time it takes a step or a fraction of a step, I need it to be really close. And I can get it down to about 1/10 of a degree by using micro steps. And by doing this, we're going to reduce the full step to 1/16 of a step. And if you multiply 1.8, which is the degree angle at which it currently moves, times 1/16, we're going to get it down to about 0.111, 1/10. Let's just go with 1/10, 1/10 of an angle. It's going to give us a lot better resolution. And it's also going to slow it down. So currently you see this thing moving really fast. It is going to slow down when I reduce the steps 1/16. We're going to see we're going to see the 500,000 micro step. That's going to go extremely slow. It's going to look very, very slow. So we're going to have to go back and change the numbers. Now 1500 microseconds, as you can see, it spins super, super fast. So once we do the micro stepping, it's still going to spin, I think, pretty fast, but definitely not as fast as it was. So we're going to kill two birds with one stone. We're going to slow it down and give us some resolution by adding the micro stepping feature. So bear with me. Here we go. All right, I grabbed 3 white DuPont wires. I'm going to hook the first one up to MS1 on the motor driver. The second one, I'm going to hook to MS2. It's going to be hard to get in there. Now, if you noticed, I have 2 motor drivers on my breadboard. In this video, I'm only using the one. The second motor driver is for the next video. That's going to control my Y-axis motor. All right, so the third wire goes to MS3. So I've got MS1, 2, and 3. All have wires coming out of it. MS1, I'm going to go ahead and grab that and connect it to pin number 9 on my Arduino. MS2, going right in order, I'm going to connect that to pin number 10. And finally, MS3 goes to pin 11. All right, we're all hooked up. All right, now I just have to add a few lines of code in my sketch program to account for MS1, 2, and 3. I'm going to start by writing constant integers again. MS1 is pin 9, MS2, pin 10, and MS3 equals pin 11, semicolon. So that's at the very top. We've declared the variables for all 3 of those pins, and now I need to go ahead and set the pin mode. So I'm going under void setup, and I'm going to go right underneath all those pin modes I've already set. And we're going to set these all to output. That's right, output. Excuse me, MS1, output, semicolon. Output. Lastly, MS2, MS3 is also output. And right under that, I'm going to go ahead and hit enter. Right underneath that, I need to digital write them all high. all caps high, and this time, yeah, we're still separating everything by semicolons. Too high. And the reason I'm setting them all high is because there's different combinations. You can go high, 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 low, 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 or high, low, high. Uh, if you look that up, there are different steps. So depending on the combination of which ones are low and high, you can do a quarter of a step or an eighth of a step. But by me setting MS1, 2, and 3 all high, that is the combination for 1/16th of a step. And as far as I know, that's the best resolution I can get. Lastly, MS3, our final one, also high, semicolon, and I'm going to go ahead and check mark that, compiling sketch, and I'm going to go ahead and upload it, and we're going to see the difference here, right here on the motor. All right, check it out. I found a solution to the arrow falling off. I've zip tied it this time to the flange, and I drew a red line on a piece of paper. If you see that red line, I'm moving the joystick slightly to the right, and you can see it just creeping away from that red line. And although it's still ticking at 1/16th of a step per high and low, it's hard to notice. It looks like a very smooth turn left and right, and that's what I want. I'm probably going to go back and change the 500,000 microseconds to something lower, maybe something like 35,000 to see how that works. But okay, this is at full speed. That's 1,500 microseconds. I like that speed. I think I'm going to keep the 1,500 where it is. That's the speed I want. As you can see, it has noticeably slowed down. That's perfect. So I'm going to keep it the way it is. Other than that 500,000, I'm going to drop that down to a lower number to make the slow part a little bit faster. Here's the code that I wrote in its entirety. Feel free to pause the video if you want to read this over, study it, or copy it. Pause here. Thank you for watching my video. Feel free to like and subscribe. In the next video, I'm going to do the Y-axis and probably the laser too. If you have any questions or comments or any ideas that you want to share, please leave them in the comments section. Thank you again and have a good day.